All right. All right. Hello. Our quandary for the day. What is binding energy? What does it tell us? Is there somebody who would like to answer this question? Nina's going to go for it. Go for it. The energy it takes to separate the nucleus all into pieces, right? Yeah? Okay, it's an arbitrary thing. We need to understand that. It's not something that really happens. Okay? And what does it tell us? Something's got a high binding energy per nucleon. More stable, and if it doesn't have very much binding energy, unstable. And there's people that we know that are like this, right? You'd say, well, he's got a high binding energy, but not so much him, right? Yeah? You know, like Ahmadinejad. Not a very not a very high binding energy, right? You know. Yeah, right. So the more energy it takes to separate into pieces, the more stable it is, right? Okay. What is an alpha particle? And by the way, when I was a senior in college, I'll tell this story. I wasn't too clear on this, and I was called on it. It's like, I should have known what an alpha particle was. I don't know. It's a thing. You know, it's one of them things that, you know. What is it? It's what? Hydrogen, not hydrogen. Helium. It's actually a helium nucleus without any electrons, right? Okay. So it's 2 protons, 2 neutrons. It's a big old thing. It's a great big old thing. It's the biggest thing out there. Okay. And what we say is that it's got rest mass. It's got a lot of rest mass. Okay. Anything with energy technically has mass, but this thing has rest mass. That is, if it's sitting still, it's got stuff, right? How about a beta minus? What is that? Also known as? This is a funny thing because we call this thing 3 different things in physics. Nina's got it. It's an electron, a plain old ordinary electron. Okay. Understand though that these guys come from the nucleus. They're made of pure energy. The nucleus goes right, and a little chunk of stuff comes out, right? Okay, which is an amazing thing that it makes an electron, which is not insignificant. Electrons, you know, are fairly large particle kind of ish. Okay, it's got rest mass. It makes that mass from energy. Okay, beta plus, somewhat more exotic. A positron is an antimatter electron. They don't last long in this matter world, right? They run into another electron and they annihilate. So we hardly ever, I don't think we detect those. We detect their death, the annihilation, radiation of annihilation. What's a gamma ray then? It's just a what? Just a photon. Just a high, but like really it's like ultraviolet, right? You know, first it has enough energy to give you sunburn, then it's got enough energy to pass through your body and give you cancer, or, you know, X-ray you, right? These things just will freaking sterilize you, right? Okay, I mean literally like kill you, like all your cells die at once or something like that. Okay, so yeah, gamma rays. In general, how do you determine the energy of a decay? We just had, that was question 24 was that. That was just a general question. In general, what do we do? Mass of the parts, mass of the whole. Yeah, so you subtract, right? Yes, we look at the mass of the pieces, right? We look at the mass of the whole, and it's like the whole is here, the pieces are here. It's like a little balance. It's like one of those little balances, right? Okay, this side, whoops, did I do it the wrong way? Yeah, I did. I drew it the wrong way. This would require energy, right? Okay. It's like the pieces are lighter, the whole is heavier, yeah? There we go, isn't that right? Yeah, so the question is, where did the mass go? It turns into energy. It's the energy of the radiation, right? So that answers question 4. How can you tell whether a decay will occur or not?
The pieces are heavier than the whole.
Yeah, if the pieces are, if they're lighter, it'll happen. If they're heavier, it won't happen. It requires the input of energy, right? So what's keeping the Earth's core molten hot? Okay, 4.5 billion years after the creation of the Earth is this nuclear decay, and this is sort of an interesting thing. Isn't this interesting, right? Okay, in order for Darwin's theory to be correct, you needed a lot of time. Okay, right about Darwin's time, I believe Kelvin calculated the Earth to be 6,000 years old, based on the notion that objects radiate energy into space, right? So you can calculate how long it would take the Earth, how old the Earth could be if it once was all molten hot and now it's just like the core is molten hot, right? And so Kelvin calculated the Earth to be about 6,000 years old, which works really well if you literally interpret the Bible in certain ways, right? And Darwin was having a hard time with that because he knew that it had to be older than 6,000 years, yeah, right? And of course, you know, the story goes that you could just look at Hadrian's Wall, which is this thing that's, you know, 2,000 years old. And these stones in 2,000 years, you know, are just barely eroded. I mean, you can see that this wall is still standing and intact, right? And that's just 2,000 years of erosion on those walls. Yet you can look at canyons and places like that where it's eroded through hundreds and hundreds of feet of stone. Yeah, just rain has done this, right? So you know, there was some notion. And of course, when Einstein wrote his paper and said, look, mass can turn into energy, and quite a lot of it, this explains how the Earth's core can be so hot. Because right now, there's mass turning into energy at the core of the Earth, right? And then this is the 5. What is the key difference that separates alpha and gamma particle energies from beta energies? Do we know? One's discrete and one's not discrete. What does discrete mean? You've seen a discrete spectrum. I showed you that you had a diffraction grating, and you saw that only certain colors of light were emitted, yes? Those correspond to certain photon energies, correct? Color is energy, yes? Okay. That's a discrete spectrum. Okay, the light from the sun is continuous. We don't say indiscrete because that means something else maybe, right? So one of these is discrete, one of them is not. Which one and why? Gamma is discrete, alpha is discrete, beta is not, because why? All right. All right. Thank you, sir. Say it again. It's because of what it is. It's because of the neutrino. Remember that, and we'll look at this in a sec, right? But it's because there's a neutrino given off with the beta decay, right? And the neutrino carries off some random amount of kinetic energy. In fact, the neutrino was just a fudge factor. They couldn't see that the beta particles never had enough energy to account for the difference in mass. And so either energy was not conserved, or there was a very hard to detect particle, and that's where the neutrino came in. So, all right.